Hello, everyone, and welcome back once again to this lecture series on aluminium based alloys and metal mantis composites.
All right. So we were discussing about this phenomena called strain aging, right? And in the past couple of classes, we have talked about the mechanism of this particular phenomena, and we have also discussed about this theory of strain aging given by Cottrell and Bilby. And according to this theory, this is about the buildup of a solute atmosphere around the dislocations which lead to this phenomena. Okay. And this buildup is dependent on the time and temperature. And considering this Cottrell-Bilby theory, we could actually derive that. And we have seen that the solute atom or the solute atmosphere buildup around the dislocations varies as t to the power 2/3, where t is the time. Okay. So here we have seen that this strain aging occurs when you load a material up to certain strain, then unload, and again reload after a certain period of aging. Okay, that's when the yield point reappears at a higher stress. Okay, but this can also happen during the deformation itself. That means even without reloading, this phenomena can take place. And in that case, when it happens during deformation itself, it is called dynamic strain aging. DSA in short. Right, so this is a phenomena which can occur in certain alloys where you have this kind of solute atoms, this kind of alloying elements which can actually catch up with the dislocations and pin them down. And as I said, this might happen even during the deformation itself. Alright, so dynamic strain aging is not good for many materials because it can lead to a reduction in the ductility, and in some materials this reduction can be quite drastic in a particular temperature range. For example, if you talk about the plain carbon steels, in a temperature range about, let's say, 225 to 375 degrees Celsius, there is a drastic reduction in ductility in this kind of materials due to the occurrence of dynamic strainage, right? And it also leads to a reduction in the fracture toughness as well. And therefore, this particular phenomena in such steels is known as blue brittleness, right? So therefore, dynamic strainaging is a phenomena which is not really desired in such materials because, as I said, it can lead to drastic reduction in ductility and as well as the fracture toughness also. Okay. And apart from temperature, the other factor which you need to consider with regard to dynamic strainaging is the strain rate. Okay, so dynamic strainaging occurs in a particular temperature and strain rate range. Okay, outside this range, this phenomena may not occur. But if you are within this range, in a particular range of temperature and strain rate for a particular material, then this phenomena will manifest in terms of this kind of serrations in the stress strain curve. Okay, and therefore, this phenomena is also known as serrated flow. Since the stress strain curve exhibits this kind of serrations during the plastic flow, right? And in case of aluminium alloys, this can even occur at room temperature. Right, and that is why we have been discussing about this phenomena because this is relevant to the aluminium alloys also. And apart from a decrease in the ductility, it also leads to some kind of surface markings on the surface of the deformed material, and this kind of markings are known as stretcher marks or stretcher strain marks. And this is detrimental for the surface finish, and therefore again this is a phenomena which has to be avoided when you talk about the surface appearance, surface finish and things like that. Okay, now let us talk about what is the atomic mechanism and what it leads to. So first of all, these stretcher strain marks appear on the surface due to the fact that when the DSA occurs, the deformation is actually localized in a band. And this kind of localized deformation was first actually observed and explained by Portevin and Le Chatelier. And that is why this dynamic strain aging is also known by their name as Portevin-Le Chatelier effect or PLC effect in short. Alright, so if you have a tensile specimen, for example, the occurrence of DSA would lead to formation of such bands, okay, where the deformation is localized. And during the deformation, this band will actually propagate along the gauge length. And this is manifested in many cases as surface marks, which are known as stature strain marks. Okay. And the other manifestation, of course, is the serration in the stress strain curve. Okay. So these are the ways in which the DSA is manifested, right? Right. So now we'll try and understand this phenomena, PLC effect or dynamic strain aging. So as I said in the flow curve, this kind of serrations appear due to the occurrence of this phenomena. So this is during the plastic deformation which occurs, or the uniform elongation that you have in the stress strain curve during the deformation process. So if you talk about the relationship between the flow stress and the strain rate, you might know that flow stress increases with strain rate, and the relationship between these two is given by a power law equation like this, where sigma is the flow stress and epsilon dot is the strain rate raised to the power m. Okay, so this m is a property which is known as strain rate sensitivity. So from this particular equation, you can say that under normal conditions, the stress will increase as you increase the strain rate, right? And you can easily explain that if you consider what happens when you increase or decrease the strain rate, right? So here you are talking about plastic deformation. So you are basically talking about the dislocation movement, because in metals, plastic deformation occurs by movement of dislocations. So if you increase the strain rate, this simply means that the deformation is occurring faster, right? So that's what the strain rate will indicate, whether it is occurring faster or slower, because it's a rate, right? It is with respect to time we are looking at the deformation, right? So higher strain rate means the deformation is occurring faster, which essentially means that dislocations are moving faster, right? Because as I said, the deformation is all about movement of dislocations. Right, so when the dislocations are moving faster and the alloying elements or the solute atoms are trying to catch them, they'll find it difficult to catch up with the dislocations when the strain rate is increasing, because as I said, as the strain rate is increased, the dislocations move faster, right? So therefore, as I said, the solute atoms will find it difficult to catch the dislocations, or they'll take more time to catch up with the dislocations. Okay. So as a result of that, we can say that the waiting time of the dislocations, if we call that as TW, so TW will decrease as you increase the strain rate. So let me little bit elaborate on this as to what I mean by this waiting time over here. So as you know, when dislocations move through the grains in the lattice, let's say this is a grain and the dislocation is moving. So let's say it has moved through a particular length L, right? So dislocations will come across different kinds of obstacles during their movement through the grains, right? And that is the waiting time as to the time that the dislocations are waiting at a particular obstacle. That is what I mean by the waiting time TW. Okay. And the strain rate is related to the movement of dislocations through this particular equation. If v is the velocity of dislocation movement, then the strain rate will be simply given by rho b v, okay, where rho is the dislocation density and b, of course, is the Burger's vector of the dislocations. Now, v is simply nothing but L by T, right, where L is the distance that the dislocation has moved, right, and T is the time that it has taken to move through that particular distance, okay. And this T basically consists of two parts. One is the waiting time, TW, and another is the time of flight. That means the time that it is taking to actually move between two obstacles like this, which are at a distance of L, okay. So if we now replace T in this particular equation over here, we get the strain rate as now generally TF is much smaller compared to TW, and therefore this equation can be rewritten as this. TF can be ignored, so this will be simply TW. Okay. So from here you can easily see what is going to happen to TW as you increase or decrease the strain rate, right? So you can see that as you increase strain rate, the waiting time is going to decrease, right? And what will be the effect of this decrease or increase in the waiting time as you change the strain rate? The effect would be in terms of the activation energy or the activation barrier that you have for the dislocation motion or for the plastic deformation to take place, right? So in this barrier, you have two components. So let's say this is the barrier that we have for the dislocation to move, right? So let's say this is the dislocation over here. For the dislocation to move, it has to cross this activation barrier, okay? So one contribution to this activation is of course the applied stress. That is one component of the activation energy, and the other one is the thermal activation, the rest of it. So under normal conditions, when there is no DSA occurring, as you increase the strain rate, the waiting time decreases, and as a result of that, with the increase in strain rate, the thermal activation will decrease because this thermal energy comes in quanta, and as a result of that, if time is less, the dislocations will receive less thermal energy, and therefore the thermal activation will decrease as you increase the strain rate, because that in turn decreases the waiting time TW, right? So since you have less thermal energy or thermal activation coming to the dislocations for them to move, you will have to apply more stress for the movement of dislocations. Right? Because if one component of this activation decreases, the other has to be increased for the dislocations to move, right? So in this particular case, the thermal activation has decreased due to a decrease in the waiting time, and as a result of that, the other component, that is the applied stress, has to be increased for the dislocations to move and the plastic deformation to continue, right? And that is why, under normal conditions where there is no dynamic strain aging occurring, as you increase the strain rate, the strength or the stress needed for the plastic deformation to occur also increases, and that is how you have this particular relationship between the stress and the strain rate. Okay. So to summarize, we can say that strain aging can occur during deformation also, and in that case it is known as dynamic strain aging, which is a result of the interaction between the dislocations and a solute atmosphere which forms around the dislocation. So such kind of interactions will give rise to some inhomogeneous kind of deformation, which is manifested as serrations in the stress strain curve. Okay, and therefore this effect is also known as serrated flow. Okay, so when this occurs, the deformation is actually localized in bands, and as the bands propagate through the gauge length of the specimen, it gives rise to those serrations in the stress strain curve. Okay, so this inhomogeneous deformation behavior or the serrated flow, the theory of that was developed by Portevin and Le Chatelier, and that is why this particular effect is also referred to as Portevin-Le Chatelier effect or PLC effect. Okay, so this is basically a result of the interaction between dislocations and a solid atmosphere that builds up around the dislocations. Okay, so when the solid atmosphere catches up with the moving dislocations and pin them down, then this deformation can get localized and give rise to this kind of inhomogeneity or serrations in the stress strain curve, as we have discussed. Okay, so what exactly happens, and what is the actual mechanism, and what is the role of the strain rate, and so on, that is something that we have to discuss in little more details. So today we have seen that dynamic strain aging occurs in a particular temperature and strain rate range. So how exactly that correlation is, with regard to this inhomogeneous deformation, that is something we'll take it up separately and discuss in more detail.
But for today, this is all I have. So I'll stop here today, but I'll see you soon again. Thank you for your attention.